Hello everyone, this is Dr. Mia again, power system, class number 3. Today we're going to talk about power factor correction and complex power flow. So, as you know that your real power in power system, as we discussed in previous classes, uh, VI cosine theta. Both V and I is your RMS values, and theta is the angle difference between voltage and current. So theta here is theta V minus theta I. So difference between voltage angle and current angles. So your when your theta or cosine theta value is 1, that if you have cosine theta value is 1, P becomes V times I. So your apparent power and real power become same. There is no angle difference between voltage and current, which theta is, that means your theta is 0, right? So that's the ideal situation. That means your real power and apparent power are the same power. That's what your power system company wants, because your real power is the only power that does the work. So any work is done by any work is done by the real power. Let's say your machine is moving, your light is giving you the lights, and anything around your household or industry, every part of the work is done by the real power. Reactive power does not do any work. So if you have reactive power in the system, that means you are not getting the complete power from the power line. All right, I'm going to get more into that in next few slides. So ideal situation is cosine theta equal to 1, theta equal to 0, and real power equal to apparent power. But it's not going to happen because we have capacitive and inductive load in the system, so that would take the current away from the voltage, and there is an angle difference that where your real reactive power comes in. So that's here. So if you have a current and voltage signal like this, you have your current is lagging by 45 degree over here. So your current is coming after the voltage. That means it's lagging by 45 degree. So that's over here we discussed in the previous classes. This is the reference. So your voltage right here and your current right here, who is 45 degree away from the voltage in lagging. So this is a lagging, but that means your current is lagging behind the voltage. So now, if you transfer this into the power triangle, so P over here is actually VI cosine theta, and your Q over here is VI sine theta, and your S apparent power is here just VI, magnitude of V and I. So this same angle over here, which is theta, which is 45 degree. So that is your voltage and current phasor diagram, and this is the so-called power triangle for P, Q, and S. All right, and this is a typical load over here. As we said before, it could be R and X, the same value. This could be 10 plus J10, right? So that's what give a 45 degree angle. All right, so what does this mean when it comes to real power and reactive power? So in 45 degree angle, your real power, let's say your voltage and current is, if we can go back to the previous slide, let's say your voltage is 120 degree, 0 degree angle. Your current over here, if we go back to the same example here, is 4.48 negative 45 degree. This is amps, this is voltage. Then your real power would be here, VI cosine theta. So you can do the math over here. Let's do the math. 120 times 8.48 times cosine 45. So that is your 719.55 watt. So that's your real power right there, if you do the math with that. All right, so again, it's and then you can find the reactive power to VI sine theta, and you can find the apparent power just multiplying V and I. So let's what you can we did the one for the inductive power. If you do the capacitive power, that your voltage is right here, 0 degree angle. So then your current would be leading for this one. So current would be somewhere here for 45 degree. This is your 45 degree, right? So then your capacitive reactive power would be negative. So that would be over here. If you draw the diagram here, this is your P, and your Q will go down here. Then your apparent power is right here. So that is your 45, and this is your S. So that would be your diagram for capacitive load. So let's go here. Let's try to make sense of power factor, okay? So let's say that you have a 5 megawatt load. So your load is consuming 5 megawatt. That's the real power. So this is the real power here. And power factor is 0.6 lagging, supplied by 11 kV single phase line, right? What is the transmission line current? So now to do that, so I know the real power, P, it will be VI cosine theta, right? Let me go back to my favorite color. So P is 5 megawatt, which is 10 to the 6, and V is 11 kV, which is 11 times 10 to the 3, right? And I'm trying to find I. And my cosine theta, which is right here, which is your power factor, is 0.6. So if I do the math over here now, your I would be, you can do the calculation with a simple calculator there. Let's see, I might have the calculation over here. So I can see that my current is 649.35 amps, right? So let's go the second part over here, okay? So let's say that if the power factor improved by this much lagging, what is the line current, right? So let's see, your power factor is, new power factor is right here. So it's still consuming the same amount of power and same voltage. And you're trying to find I. Now your power factor is 9.5. So your I would be 478.46 amps, right? So now what is this means? So let's say that, so you have a load over here. I'm going to draw this over here. That's your 5 megawatt load, right? Then this is your transmission line coming out here, all right? And this is your 11 kV across the load, right? So this is your 5 ohm transmission line supplying all those things. This is the current coming out here, okay? So you as a consumer, you're only paying for whatever you're consuming at the load point. You're not caring about what's happening at the line. So what is the line loss now? Both cases. Line loss, this one is be I squared R, you know this equation. So if I do this equation for I squared R, for this one it will be 1.14 megawatt of power losing in the line. And for this one here, you have I squared R will give you 2.11 megawatt. So look at the loss. See, this loss almost doubled if you have a low power factor. So low power factor loss almost double. High power factor loss, you almost saving half of it. So what's happening, your power factor improvement at the load will draw the less current from the line to do the same work. So still, we're doing the same work here. We're consuming the same real power, same work, but with the low power factor, we're losing too much power in the line because we're drawing really high current here. And for the high power factor, we're drawing less current, so we're losing less in the line. So that's why power system company want the higher power factor at the load end. Otherwise, they're going to penalize you for the low power factor. All right. So power factor is very important to reduce the loss in the transmission line. And so how do you do power factor correction? Normally, is it always true for the load that most load are inductive? Look at the load. At industries, all motors. Motors are big inductors, right? And also at your home, you have any HVAC systems or any kind of things running, moving fan, AC, your pump in the refrigerator, all are inductors. So load are normally inductive. So this is what the natural load look like. So what the goal here, the power factor correction, to bring this angle together as close as possible. So goal for the power factor correction is to bring the angle as close as possible, right? So I1, this is new angle over here after correction. So I want my angle close to 0 possible, right? So then to do that, I have to take this mass off of inductive load. To take the inductive load, I have to add capacitive load. So this part is the capacitive load here. So goal is to add capacitive load. That means adding capacitor in parallel with the load. So that where you take the lagging power factor reduced to close to 0. So what I'm doing here, so you have, let's say you have a load over here, which is by nature inductive, then you have a lower power factor. You basically bring a capacitor in parallel to the load. So you're gonna draw less current here. So current will be less after you do the power factor correction, because your power factor, overall combined power factor here is improved. So then you draw less current from the line to do the same work. That means you're basically reducing line loss for the power system company. So power system company wants to see your power factor 0.9 or higher. We're going to do this problem in the class to show you basically how it's done. So we're going to get to the class and do it. I'm going to see you another video for this lecture, which is complex power flow. So we're going to stop here for the power factor correction. We're going to do this problem in the class.